So what we're going to do now is we're going to start talking about the next category of API method groupings in the Completable Futures framework, and this is the completion stage method category. And as you can see from this pie chart, that represents the bulk of the methods in Completable Futures. And completion stage methods chain together these dependent actions that are used to perform async result processing, and at least some of them can also be used to perform simple types of composition. There's other more powerful types of composition that are provided by arbitrary arity methods, as we'll talk about later. So what is a Completable Future completion stage? Well, as we talked about before, there's an interface called completion stage, which I strongly recommend you read the documentation for, because it really helps to explain in very nice depth and well-written prose what completion stages are. But basically, they are going to be the target for dependent actions to handle the results of asynchronous computation processing. That may be mystical when it's read like that. So let's take a look at an example to make it more clear. This particular example, again, occurs in the EX8 folder in my GitHub repository. So completion stages are basically used to have dependent actions that are run or triggered when a previously invoked asynchronous call completes in order to continue to process its result in a nice fluent manner. And this particular piece of code here illustrates one such example. We'll talk about these examples in more detail later, but just want to give you the bird's eye view here. So what we're doing here is we're making ourselves a big fraction. And as you can see, it's got a very large numerator and a very large denominator. And we're using the value of factor method, and we're passing a flag in that says false. It says, don't reduce this big fraction. Just make me a big fraction that's unreduced. And then we go ahead and we make ourselves a supplier lambda variable that, when used in the context of supply async, as we'll see in a minute, can be used to reduce this big fraction in the background. And that's the key to this whole thing. Reductions of big fractions take a while to run, and so we don't want to use the foreground thread to do that, because that'll block the main user interface thread and will degrade quality of service and degrade responsiveness for the program. So then what we do, and here we can use our factor method we talked about before, we can use the supply async factor method, and we can pass it in the reduce supplier variable. So we're passing in reduce. And what that'll do, as we just saw, is that will go ahead and arrange to execute the reduce supplier in a background thread in the common fork join pool. Same as we just looked at with the factor method discussion. Okay, so far so good. What comes back from supply async, of course, is a completable future. And what we do then is we chain together a completion stage method, which in this case is a very simple one called then apply. And what happens here, the way to think about this, is that then applies action, which in this case is the method reference big fraction : to mixed string. It arranges to call the big fraction to mixed string method reference or method on the result of doing the reduce in the background when that asynchronous computation completes. So that's what a completion stage method is about. As the name implies, it is going to be called when the previous stage completes. So when the completable future from supply async is done, meaning that we've reduced the fraction, we then go ahead and apply the to mixed string method in order to convert the improper big fraction to a mixed big fraction. And then what we can do then, just to continue on with our fluent chaining, we can then apply yet another completion stage method, in this case one called then accept. And what then accept does is it gets triggered when the previous stage completes. So after we've converted the improper fraction to a mixed string fraction, we're then going to accept that result, and the action that'll be called for then accept will print the mixed string out to the standard output. So you can see how we're basically chaining all these things together. So when something occurs in the previous stage, then the next stage in the chain gets a chance to run. As you can see here, each of these different completion stage methods, and for that matter, supply async, which is a factor method, will register or arrange for a an action to be run, which in this case are lambda or method references. So you can see reduce is one action, big fraction to mix string is another action, system.out println is yet another action. Those are all basically registered with the framework. And a lambda action is only called after its previous stage completes successfully. We'll talk later about what happens if things go awry, if things fail. But be aware now that if they complete successfully, then the next action in the chain will be called based on the completion stage method and the semantics that it embodies. And this is what I mean by chaining. When I talk about chaining things together, I mean using these fluent interface styles to say, do supply async, get back completable future, then implicitly call then apply when supply async finishes, chain that together. And then when that's done, we chain together, then accept, and so on and so forth. And this should look actually quite a bit like the fluent interfaces we've already talked about in the context of Java streams. It's just that the underlying mechanisms here are designed to be more asynchronous than Java streams, which are designed to be synchronous. And just wait till we combine Java streams with completable futures, and you can see how you get the best of both worlds. It's really cool. So basically, when you call one of these methods, when you call one of the completion stage methods, or you call a factory method, it actually doesn't do anything right away. It's deferring that action until the previous stage, or in some cases, stages, complete. And there's something that available to run that action. You need a thread from somewhere. It could be a fork join thread, as a common fork join thread as it is in this case, or some other thread if you're using a different pool of threads. One of the things that's really, really, really cool about this fluent chaining model is it enables asynchronous programming to look essentially the same as synchronous programming. So when you look at this code at a glance, it's not really all that obvious that asynchronous stuff is taking place. It really looks more like we're reducing something, then we're turning it into a mixed string, and then we're printing it. And the fact that this may be running in a background thread, and that background thread is managed by a common fork join pool, it's really kind of an implementation detail. It's a very important detail, of course, but from the point of view of not blocking the caller. But you don't have to know, you don't have to care about how the mechanisms work under the hood. You just have to know what the semantics of the framework are and what kind of behavior you can expect if you use the code chained together in this particular way. So why do we do all this stuff? What's the whole point of this? Well, the whole point of this is to avoid blocking the caller thread until we really, 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 really need to get the result. So it turns out that you don't want to call join, or even worse, get, unless and until it's absolutely necessary. And that's because the moment you call join or get, now you're putting synchronization into your program, and that's going to start underutilizing the available parallelism and make things run more synchronously than they probably need to. And that, of course, then improves responsiveness by not blocking the calling thread. The calling thread can be doing other things, responding to other kinds of events through other means while these computations occur in the background. And the way that this works, of course, if you're starting to use this for client-server style programming, which is very, very popular nowadays with frameworks like WebFlux, which is part of the Spring platform, where you can have client code run asynchronously, you can have server code run asynchronously, and you can basically avoid blocking almost entirely. And the way that this works under the hood is by using something called the asynchronous completion token pattern. And that's something that I documented years ago that are probably worth looking into if you're curious. So click on that link if you want to learn more about that particular pattern. So completable future can then serve as a completion stage for async result processing. And you can see here some of the examples of some of the methods that are commonly used for completion stages in the completable future API. So we have then apply, which we've seen a little bit of. We see then accept, which we've seen a little bit of. We'll see some other ones later, like then combine and then compose and so on and so forth. And these are all very cool, very powerful methods that we'll look at in great detail as we get further along in the discussions about completion stages. When I think about completion stages and completion stage methods, a certain metaphor comes to mind that I really like, and that is the metaphor, the analogy of juggling. So if you're a juggler, then you know the intent of juggling is to try to keep as many things in the air, balls, chainsaws, knives, whatever you're juggling, bowling balls, and you try to keep as many of these things up in the air as you can, and you only hold them in your hands long enough to transfer hands if you're doing two-handed juggling, and then you want to throw them back up in the air right away. So if you're doing one-hand juggling, you can do the same thing. You just have one hand. But the idea is you want to keep a lot of stuff up in the air. Same thing is true with asynchronous processing. As much as possible, you want to keep computations running asynchronously in the background and only process them synchronously long enough to start up the next asynchronous operation in the chain. And why this is useful is it ensures that you only consume resources when an action runs, which will thereby reduce system overhead. So you won't have to sit there and block. You won't have to sit there idling and blocking. You're only going to be doing computation when something's actually running. And maybe a good example of that would be automobiles that are especially popular in countries like Europe that have these so-called start-stop systems. When you stop, it turns the engine off. And only when you start up again does it turn it back on. So that's a good example. Idling at a stop sign or a stoplight with your car engine running is kind of like a thread blocking when it can't make forward progress. You're still kind of tying up resources and you're polluting the system in some ways, a bit metaphorical, of course. But that's kind of the way to think about it. So by keeping things running asynchronously, then you have less issues when you need to block. So that's the end of the overview of completion stage methods. We will cover lots more about completion stages in upcoming videos, but I want you to kind of get the big picture view of what they're doing. And then as we go through the different examples of completion stages, you'll see that they're all just basically variations on this common theme.